Hi, welcome to Weekly Physics in CSZC with Sir Dan. Today we're going to talk about the other parts or remaining lessons in electrostatics 2 or static electricity part 2. And what are these topics? We're going to talk about electric potential, and particularly we're going to highlight potential difference. Then we're going to talk about capacitance and capacitors, and we'll talk about dielectrics. So let's revisit one by one these different topics in electrostatics too. To begin with, let's begin with electric potential. First, before understanding what is electric potential, we need to understand first what is electric potential energy. So electric potential energy is defined as the amount of work done by a certain charge. And work, this work done by a certain charge is caused by the attraction and the repulsion of the charged particles. Remember, when we talk about work, this is the amount of force present as we move a certain object. So if there is a force present in a certain system and that force causes a displacement of a certain body, then there is work done. Now, since we are talking about electric charges, then we consider our body as electric charges. Now, when two electric charge are present or charged materials are present in the system, that would cause the attraction or the repulsion of a certain system. And if we test a and if we test the attraction and the repulsion of these certain materials, we also use electric field. Remember that electric field is defined as the amount of force present in the system with respect to the test charge or Q naught. Now, we're going to use the same principle, testing the electric field of a certain system as illustrated here in our diagram. Now, notice that there are two conducting plates, and these conducting plates are metal objects, and every conducting plate has different charges. We have positive conducting plate and a negative conducting plate. Remember that electric fields or electric field lines can be illustrated using arrows that begins with a positive charge towards the negative charge. So that's why we have here the direction of our electric field is going downwards. So now, basically, we have two different conducting plates, two different charged particles, then they are attracted to one another. Now, if two charged materials or conducting plates are attracted to one another, then to fully verify that there is an attraction, we need to place a test charge. Now, by putting a test charge in between two conducting plates, we can verify that there is a force present, the force that allows the two conducting plates to be attracted to one another, and it will test also the electric field present in the system. Now, as we go along with this, what will happen to the test charge? The test charge is being, say, the test charge is a positive charge, it is being pulled by the negative plate, or it is attracted to the negative plate. Having said that, there is an electrostatic force present in the system. Now, if two conducting plates are attracted with each other, there is an electrostatic force between those two objects, or with those two charged materials, right? Now, if there is a force present, then they are attracted to one another, they are displaced. Now, electrons will be the electric charges will be attracted, then it will be displaced by a certain distance r. The same is true with this one, as we have illustrated here in our diagram. These two are attracted with respect to a distance r. So from a point A to point B, there is a distance r. Okay? And if there is a force present and it is presenting a displacement r, By virtue of the work energy equation, work is equal to the amount of force multiplied by the displacement r that will give us the work done, and the work done is energy. If there is energy, and and since we're talking about static electricity, electric charges are at rest, then the energy present in the system is a potential energy. And since it is in a form of an electrical object or electric charges, then we can define it as electric potential energy. Electric potential energy is just, as we have said a while ago, is just the potential energy present in the system where there is work done by the electric charge, and the work done is caused by the attraction and the repulsion of the electric charges. Now, how do we use, what's the significance of electric potential energy to electric potential? Now, since we are talking of electric potential energy is the energy present in the system, electric potential, on the other hand, is the amount of electric potential energy that is being exerted in the system with respect to the test charge. So we tested that there is a potential energy in the system, and we tested it using a test charge so that we can be able to identify that there is electric potential. We need to isolate or identify the individual potential energies with respect to points A and B. And mathematically speaking, it is presented as the potential difference from point A to point B. Now, why from electric potential we have mentioned potential difference? Electric potential refers to one electric potential at a certain point, while potential difference talks about the difference between two electric potentials from point A to point B, or from an initial to a final electric potential. Now, if we go back to our illustration here, we have 2 points A and B. At point A, there is electric potential energy present. And then at point B, there is also an electric potential energy present. Now, we have tested this electric potential energy by means of placing a test charge. Now, if we place a test charge into the system, we can identify that there is really electric potential energy present. Now, if we want to find the ratio, or we want to find the electric potential by means of the electric potential energy and the test charge present, what we can do is that we can get the ratio of the electric potential energy and the test charge itself. Hence, we have the initial point and the final point. Let's say, for example, that point A is our initial point and point B is the final point. So, since we are going to get the potential difference, so we are going to subtract point B from point A. So, final minus initial. So, we have here potential difference V sub B minus V sub A. Now, what is V? V is a representation of electric potential. Okay? Now, electric potential has also another term aside from potential difference. It is also known as the voltage of the system. So there are three terms that we can associate with electric potential. First, electric potential itself, potential difference, and voltage. But they are just the same. Okay? But primarily, we are calling it voltage. We are using voltage if it's already moving from one point to another. If it's in static position, or if it's in if the electric charge is at rest, we call it as electric potential because of the potential energy present. But once it is moving, then it is now gaining kinetic energy, then we can call it as voltage. Now, having said that, we have able to identify that the potential difference in the system is between 2 points, final and initial points, V sub B and V sub A. Now, the potential difference or electric potential is defined as the electric potential energy divided by the test charge itself. Because why do we have a test charge here? As I've said a while ago, we are testing, we have used a test charge, or we use a test charge to test the electric field. And since there is an electric field, there is a force of attraction, then there is electric potential energy present. Now, so the difference, we can also write this as the work done. Okay, since energy is also can also be written as form of work, we can also write here negative work done from points A to B. Now, so the question is, in this side of the equation, it is positive, but on this side of the equation, it is negative. Why? Primarily, primarily, this is also because of having the direction of the electric charge. Now, if we take a closer look on this example, we can also say that the electric charge is moving what towards each other, right? The electric field is what moving from positive to negative. So it's from a higher position, a higher potential, down to a lower potential. That's why we have used here a negative connotation of the work done from A to B. Because remember, uh, the negative charge has a lower potential, and the positive charge has a higher potential. Okay? This is in a form of a work done equation. But what we are using for the sake of presentation, what we can use is in the energy equation, energy U. Now, since it's difference, we can simplify this equation as the potential difference between 2 points that is tested by a test charge here. So we have here delta V is equal to delta U. Now, what I want to do right now is to derive an equation that would simplify electric potential energy. And how do we do that one? How do we derive an equation that would simplify electric potential energy? So we can write here, let me use a black ink, say that the potential energy, so let's isolate one potential energy. We say that the potential energy V is equal to the electric potential energy U all over test charge. Now, what do we know about the electric potential energy? Electric potential energy is U, or the work done is just F all over U D, or I'm more comfortable of using R. Okay. Let me, this is U, electric potential energy U, or also work done, right? Now what we can do is we can substitute this one. Okay, we can substitute this as FR all over U. Now if we're going to substitute this one, we can have V is equal to FR all over Q naught. Now what is F? Right? F is, what is F? F is our electrostatic force. And electrostatic force is defined as F is equal to K, the Coulomb's constant, times Q1, Q2, all over the square of R. Okay. Now, if we are going to substitute So we have here F, an equation F here. We can substitute this equation to F here. And how do we do that? We can write it as V is equal to K Q1. Now remember we have Q here. We tested it using a test charge. So there is an attraction between the charged particle and the test charge, an unknown charge and a test charge. So we can write this as Q naught, okay, all over R square, all over Q naught. But I can simplify this. I want to write this in a simple manner, which is also equal to, so I'm going to get the reciprocal of this one, K Q naught. We can write this as K Q times Q naught all over R square, R square okay. We still lack one R here. We have R times R times 1 all over Q naught. Now, having this equation here, we can simplify this equation. Yes, am I right? So if we can simplify this equation, we can simply use it as, we can write R square as RR, right? If we write RR, R times R, we can just easily simplify this equation. So let's simplify the equation. R divided by R, that's equal to 1. That would cancel out. And Q naught, we have two Q naughts on this different side of the equation. If we cross multiply this one, this will also give us 1. So what is left with the equation? What is left in our equation is electric potential V is equal to Coulomb's constant times the charge all over distance R, okay? Which is also equal to the electric potential energy of the system all over the test charge Q naught. So these are the two equations that we can use to determine the electric potential of a certain system. Let's say this is equation number 2, and this is equation number 1. Now, let's try to revisit. So to further understand this one, I have here two illustrations that would allow us to understand deeply on electric potential and electric potential energy. Remember that the work done is uh, the graduate. There is a uniform gravitational field. That is when we are finding the gravitational potential energy. So if we have 2 points from a highest point and to the lowest point, we can have the gravitational potential energy. If we apply this same concept in electric charges in two conducting plates with a point charge that is placed in between two conducting plates, and these two conducting plates have uniform electric field. Now, the electric field here is the pink arrows, this one. And remember, the electric fields are perpendicular to the surface of the conducting plates. Now, it's always the it is always noted that the electric field is parallel to the direction of the point charge. Okay? It's always denoted as parallel to the direction of the point charge. Now, this point charges has also lines. Right? We can illustrate also the direction of the electric charges using equipotential lines, which is just similar with electric fields. Now, as you can see, the amount of force present that is caused by the attraction of the charge is parallel to the electric field. So if we compare these two illustrations, they follow the same concept. If an object is moving in a uniform field, then the electric potential energy is also moving on the same electric field, well, from the higher potential to the lowest potential. Now, in electric potential energy, the point charge always moves from the higher potential energy, from the higher potential to the lower potential. Now, let's put the equation to the test. I have here a source charge or a point charge, and assuming there is an unknown charge present in the system, and the source charge and the point charge is measured at a certain distance from the charge. Now, your task is to define or to identify the electric potential of the source charge. So how do we do this? So we have two source charges, positive 4.3 times 10 to the 3 coulombs, which is separated by the distance of 7.11 times 10 to the negative 12 meters, and negative 2.33 times 10 to the negative 13 coulombs, with a distance of 6.45 times 10 to the negative 15 meters. So, what is the electric potential of the source charges? Now, if we revisit our electric potential equation, V is equal to KQ all over R, where K is our Coulomb's constant, Q is our charge, and R is our distance. Now, let's try to substitute the values. Now, the values here, we have the Coulomb's constant, we have the source charge, and the distance. Now, after substituting the values, we can just simply go directly to in simplifying our value. So we multiply Coulomb's constant and the charge, and then we divide it by the distance r. So if we divided the variables, we will have a small letter V in honor of Sir Alessandro Volta, the one who dedicated his time in studying electric potential. Now the same process will be applied in number 2, or in the second problem, wherein we substitute the values, Coulomb's constant, the source charge, and the distance from the source charge. And if we follow the same process in number 1, or in problem number 1, we will have an electric potential of negative 3.248 times 10 to the positive 11 volts. Now the question is, why do we have a negative potential here? Because the electric charge is negative. Now the electric potential is always directly proportional, or is directly proportional to the source charge. Whatever would be the sign convention of our point charge or source charge will be also the same with the potential, or the electric potential. And the electric potential is inversely proportional with the distance r. Are there any questions? Great. If there are no more questions, then thank you for joining me in this session on electric potential. But if you still have questions that would come into your mind after viewing this lecture, feel free to comment down your questions and I'm going to answer it. So thank you very much for joining me here in Weekly Physics in CSZC with Sir Danny. I'll see you on our next lecture on capacitance and capacitors.